Welcome back. So now let's try to get that example grounded in these with these notations and languages. Yeah, I'll do that and then we will go to the density functions. Okay. Now recall that in the previous session I told you that from a probability perspective, probabilistic perspective, the entire process of uh, imaging and assigning a label to it can be seen as assigning a random variable, and once we do the measurement, the actual measurement that we do, okay, the one that we get in our computers, they can be seen as elements from the range space of this random variable that we are looking at, and there always exists an underlying probability distribution function or the probability measure which has been imposed by the random experiment. Remember that, right? You remember that. Okay. So now let us consider an image. So let us take an example. So consider an image. Of dimensions p cross q, okay, p where p q are arbitrary numbers. Okay, let us say that we have this image. There are, so remember that an image is represented as grid of p q numbers in a computer. Okay, when you read an image using OpenCV or any kind of softwares, what you get is a matrix, two-dimensional grid with p q numbers, and there are p q pixels as each of this each of the entry in this PQ grid is called a pixel, and there are PQ pixels. Now this for our purpose, okay, is can be seen, can be viewed as a R PQ dimensional vector. If you stack all the rows of this image and make it a long image, long vector, this is a vector in RPQ dimensions, and this PQ is what we are calling as D. In general, an image is a D dimensional vector. Make sense? Okay. In general, any data point, okay, data point is a D dimensional vector. Okay. So now in the probabilistic viewpoint, this RD is actually the range space of the underlying random variable, which means every data point that we have, or rather every image that we see, okay, is an element in the range space of the underlying range space of some underlying random variable that we are interested in. Okay. So every image or every data point is an element in the range set or range space of a random variable. You understand now? Question?
I didn't get how it is PQ. I mean, it is a rectangle in PQ dimensions. How is it a vector?
Okay. See, the question is how is that a vector? I mean, see, you represent an image as a rectangular grid of PQ pixels, but what you can view that as a vector by stacking all the rows of this matrix one after the other. So you get RPQ or rather PQ number of pixels. So you take PQ is your D. So an image is converted into a D dimensional vector.
You're mapping it to PQ dimensions.
Not mapping, I mean it is, I mean you are viewing that as a PQ dimensional vector, that is it. Yeah. See, in fact, as we move further in the course, I will show you that all the data points that we get in practice, right, an image, I already gave you an example, right, of how a text can be viewed as a d-dimensional vector, and we will see more examples as we move on. But to concretize the idea, let us now start with one data type, which is an image, and which is a d-dimensional vector for all practical purposes. But what's important is the following, right. So every data point is an element in the range space of a random variable. This is the take home message, this is the viewpoint that I want you to have. Question? Yeah.
So, can you also explain like how would the event space of that particular random variable look like?
Good question, I will tell you. That is the next thing. The question is, what would be the corresponding event space, or rather the sample space of the underlying experiment? Okay, it is open for interpretations, because I told you that the random experiment is something that the user conceptualizes. Okay, there is some experiment that is happening, and you get some outcomes. So these outcomes are observing these images. Okay. Now if you see an image as a d-dimensional vector in the range space of a random variable, what is that random variable doing, intuitively, is that it is measuring the likelihood of getting a particular value for a particular pixel. That is what it is measuring. So it is telling you that, okay, okay, for ease, let's view this as d scalar valued random variables for now, because I told you that both of them are equivalent, right. A d dimensional vector valued random variable is equivalent to having d scalar valued random variables. Now let us say that you have one random variable, and suppose you have what is called as a single pixel camera, where you are only getting one pixel. Now what is this measurement giving you? This measurement is telling you, when you do the measurement, the surface will give you correspond to some value of the pixel, right. What is it telling you? It is telling you, suppose I measure, I take the picture of all of you sitting here, okay, and suppose there are 100 of you in the class, and I get 100 values. Okay. So these are 100 realization of the random variable, right. So basically I am getting 100 points from the range space of the underlying random variable. What is it telling me? So this is telling me that when I conduct this random experiment, what is the likelihood of observing this particular value from that experiment that I am conducting? That is what the correspondence is. Make sense? Right. So as I told you, why are we doing this? Remember that we are doing all this jugglery because we do not know the physics of the problem. The whole point is repeated experiments and use statistics to model. Okay. Now this random variable is giving you the measurement. Okay. Yeah, a little bit of correction in what I said. The probability measure, the underlying probability measure or the distribution function is telling you what is the likelihood of obtaining this particular pixel value when you conduct this random experiment. That is what it is saying.
So, if I may extend it, so all this q vectors would be stacked one by one, right?
Mm.
And one of the pixels would be ranged from 0 to 255, and we normalize it to 0 to 1.
Does not matter, yeah. Let us say that you normalize, see the value that it takes does not matter actually, but let us say that you normalize, so what?
No, I mean without normalizing, how would you say that it's a probability of getting?
Oh, see, okay, I see the values of this vector is not the probability. So remember this, right, every data point is an element in the range space of random variable. The element in the range space is not a probability. Please be very clear about this.
It's a real number.
It's a real number. It's a real vector, it's a real number. The element of the range, because the range space of probability, range space of random variable is always real numbers. So the actual value of the data point that you see does not correspond to the probability at all. It has nothing to do with probabilities. What is a data point? A data point is an element from the range space of the random variable, that is it. Is all of you clear about it? This is very, very important, okay. But since there exists an underlying sample space, there is a probability measure that we have defined on the sample space. See, always remember that the probability measure is defined on events, okay. So, when you have the random variable, you can talk about the inverse image of this random variable in the event space on which the probability is defined. Okay. So, the values that the data points take has nothing to do with probabilities at all, they can take any value, it need not be 0 because it's just RD, it's just real numbers, you can take any value. Is that clear to all of you? It's very important. Okay. But yeah, so this is every data point is an element in the range space of random variable, this is important. The other important observation is that the distribution, let me call this of a random variable x, okay, the distribution function indicates or rather quantifies the likelihood of observing a data point under x. View x as some observations, right. So, when you observe, there is a likelihood of this because every observation that you make, every single element in the range space of the random variable corresponds to an event, or rather I mean that is not mathematically correct. If you have continuous random variables, it is you should take a subset of the values in the, or you should consider a subset in the range space. Every subset in the range space of the random variable corresponds to, has an inverse image in the sample space. So, that has an underlying probability measure. So, what that probability measure talks about is that what is the likelihood of seeing this particular event, right. What is an event in this particular case? The event is obtaining that image, event is obtaining that image. So, what do you mean by obtaining an image? Having these particular pixel observations. So, the distribution function, okay, ultimately tells you what is the likelihood of obtaining this particular image under this random variable. Do you see the point? Okay. So, the moral of the story is the following, that if you can estimate the distribution function, okay, then you know everything about the underlying sample space. See, that is why they say that the distribution function completely specifies the sample space, because if you know the distribution function, right, you can know everything that you are supposed to know about the underlying experiment. Okay, let us write that. So, distribution function completely specifies so this is the key observation. Okay, distribution function completely specifies the underlying sample space. Do you understand why? Is this clear? Because this is very important, take a moment to understand this if you do not ask questions. So, now these again I will trace back. So, there is an underlying experiment, random experiment that is happening. There is a probability measure that we have defined on top of the sample space, and when we measure, we assume that there is a random variable, a function that will take the elements of sample space and maps it to real numbers, and that is what we are seeing, and that gives rise to, that translates the probability measure onto the distribution functions. Okay. Now, what does the probability measure tells you is that what is the likelihood of obtaining this particular event, that is what the interpretation of the probability measure is. Now, the same interpretation holds true for the distribution function as well. So, distribution function tells you what is the probability or what is the likelihood, let me not use the word probability, what is the likelihood of obtaining this particular image, if I may say that. Okay. So, now if we know what the distribution function is that is generating or rather giving rise to this particular observation, then we know everything about the sample space. Now, this is the statement that we will be justifying and creating algorithms for in this entire course. Now, this entire course is about estimating distribution functions of different forms given observations from random variables, because that will tell you everything that is that you need to know about the underlying experiment. So, now an engineer has to design the scenario in such a way that his or her problem fits into this narrative, in the sense that you tell me what the underlying sample space is, okay, you identify what the underlying random experiment is, and then design your data or get your data accordingly and design your problem accordingly, and then you put an algorithm to solve that problem. Okay. Now, if you can see, okay, so let me tell you, one other point just to drive home the message. Now, we said that in this example there is an image, right, there is an image which can be seen as a d-dimensional random variable. See, when I say an image can be seen as a d-dimensional random variable, please remember what am I saying, okay. I mean that an image is an element in the range space of a function called the random variable, which has been defined from sample space to real numbers, that is what I mean. From now on I will just say that an image is a random variable, that is a wrong sentence, yeah, but I will still say that assuming that you understand what I mean, okay. And if you see in some books or some research articles or somewhere where people are saying that consider a random variable and the data that we have are observations from random variable, this is what they mean, okay, right. So, now we said that an image is the image is an element from the range space of a random variable, but our problem also had labels, you remember, because the entire random experiment was that somebody's X-ray was taken and some label was assigned to it. How do we model this? We model this as joint distributions. So, label is considered as another random variable that is attached on top of, or rather another random variable that is defined on the same sample space. You see the point, right? So, in this example, so distribution function completely specifies the sample space is a true sentence, right. So, suppose you have one other random variable that is defined on the same sample space. See, calling it a label is an interpretation. Mathematically it is another random variable that you are defining on the same sample space. So, the entire experiment is an image is being taken and a label is being assigned to it. So, that entire thing is now modeled as two random variables, one which corresponds to getting the image, the other that corresponds to assigning a label. Make sense? So, typically, so this is only a typical thing. So, that is why I will tell you, typically a label is taken to be another additional random variable defined on the same sample space. This is the typical case, okay. See, just I told you in the first class that I am a generalist, right. I like seeing things from a very abstract manner, right. So, you will see this now, I hope that some of you will appreciate this. See, I do not I generally define terms like supervised machine learning, unsupervised machine learning and so on, okay. To me everything is a special case of distribution estimations. I will tell you why. Even the so called supervised machine learning can be seen as unsupervised machine learning, I mean it's just an it's just nomenclature. I'll just tell you why they are this, they are same, they are so. But yeah, so before I come to that, so you understood, right? Typically what happens is that you model the label or an additional take another random variable and call that a label. That's just a semantic nomenclature. Okay. Then what happens is, so in this scenario,
So do we like map that to RD as well?
good question. I'll tell you. In this scenario, we have two random variables, x and y. X is in RD and y is in RK. Okay. This is the most general definition, right? Y can be in RK. So you want to have binary labels, you make your R to be 1, right, and all your values are coming from a subset of R which is between 0 and 1, or you can even make it discrete, right, or you can make it a set of this thing, close 0 1, right. Now suppose somebody is doing this, somebody is taking an image, okay, and the task is to localize, okay, a tumor in an image. So there is an X-ray, okay, and there is a there can be possibility of some tumor in that X-ray. Your task is to identify where the location of the tumor. Now how do you identify the location of a tumor? The typical way to do it is that you put a box around it, okay, and you give the coordinates of that box. Every rectangle in an image can be represented as represented using 3-4 numbers, right, the center, the height and the width, okay. Now there what happens is there is an image and 3 numbers corresponding to the location, the height, width and the center of the box. So in that case your k is 3, make sense, that is it. So if you have 2 labels 0 and 1, then your k is 1 and you have 0 and 1. Suppose you have, instead of having 2 labels, suppose you have 5 labels, then what happens? 5 categories. Then your y will become discrete 0 1 2 3 4 5. It is not RK, it is this set, right, it is. Always remember that whatever this thing is, right, x and y, they are the codomains or range of the function that we are talking about. So basically what is happening, so I am repeating this 100 times because this is the most important thing that has to get across. Once this idea is clear, everything else is only an algorithmic extension on top of it, but this is the key understanding that I want you people to latch on to, okay. Is this clear? Okay.
In case of disease and disease, it can just be two valued.
It can be, yeah, discrete 0 1 1 2 or whatever. See these numbers they do not have any significance per se, right, I mean unless they correspond to some measurement or something. Typically in a discrete case it is just some categorization, right, so belonging to A or B or 4 5 categories and so on. Is this clear? Now what happens is, so because we have 2 random variables, there is a joint distribution, okay. Now the nomenclature is, the notation or convention is as follows. Say that a data set, so learning, I have not defined what machine learning is yet, okay, I will define that later, starts with with a data set. Data set D, which is a set of tuples of this sort x1 y1 x2 y2 x3 y3 and so on x and yn let me make this capital. So you start with a data set, okay. You have n images and all of these images have some labels, okay. So I should also say this. So X is typically called the data space or feature space or data space. Y is generally called the label space or action space, label space, nomenclatures.
Sir, specific to the X-ray example which you gave, how can we visualize that sample space? How?
I'll come to that just a second. So you have data set, which is a set of tuples of form xi comma yi, and you have n of them. So it is said that this is sampled, so there is a tilde that is written, it is sampled IID from an underlying distribution, joint distribution Pxy. Okay, this is the conventional nomenclature. So I have introduced a new term here, IID. Okay, what is this IID? We will see in the next lecture.